going to start with ordinary differential equation, first order, of y prime minus y equals 0. And in this case, I'm also going to give an initial condition where y of 0 is equal to 3. Okay? So the way we're going to solve this is we're going to first look and see if we can do separable ordinary differential equations, because those are the easiest. We like those a lot. So let's see if we can isolate all of our y's on one side and all of our x's on the other. So the first thing we need to do is turn this y into our Leibniz notation of dy dx. And then I'm going to, at the same time, I'm going to go ahead and add y to the other side. Right? Well, now I see this is pretty clearly separable. This should be pretty straightforward. I'm going to multiply this whole thing by dx over y. Right? So multiply by dx over y here and dx over y here, and I'll end up getting dy divided by y is equal to dx. Okay, great. That's separable form. We're looking really good. So now we can take an integral on both sides. So the integral of 1 over y dy is just natural log of y. And then our integral of 1 dx is just going to be x. These are indefinite, so we need our c. Okay? Now we want to isolate for y, especially because that's what our original target was, and that's what our initial condition is in terms of. So when we isolate for y, we're going to multiply everything, or we're not going to multiply, we're going to take everything e to the power of what is here. So we have e to the power of the natural log of y is equal to e to the power of x plus c. Now we know e to the natural log cancels out, and whatever's inside comes down. So we have y to the first power, and on this right side, this e can distribute across the pluses to all of its x's, and they become multiplied. So you get e to the x and e to the c. Right? Now remember, e to the c is just a constant. So we can actually just turn that into another constant and put it at the front. So now we get y, I'm going to make this one a little clearer that it's a 1. There we go. So we just get y to the first power, so just y, is equal to c e to the x. Okay? So this is our I think it's called inexplicit. And then this is going to be our explicit form. And this is our general. And now our particular is going to be where we plug in our initial condition. So we're going to plug in a 0 everywhere there's an x, and then we're going to plug in 3 for our value that we're solving for. So we have 3 equals c e to the 0. Now e to the 0 we know is just going to be 1. So we're just going to get c is equal to 3. So now we can go back and plug that into our original equation. So we get y is equal to 3e to the x. And that is our particular solution. So let's start with this equation here where we have dy dx is equal to 1 plus e to the 2x. Okay? That is one of the, yeah, okay, good. So for this one, it doesn't really look like it's separable at first. But if you notice, there's no y's on this right side. So we actually do have a separable thing. So all we have to do is multiply this dx over, and we're done separating. We can go straight into our integration. So we have dy here, and then we're going to have 1 plus e to the 2x dx. And then we can add our integration symbols, and then we can just do our integration. So here we just have 1 dy, which integrates to y. And then here, this one's not horrible. It looks a little weird, but it actually works out pretty nicely because you can distribute your integral across your addition sign. So you just get the integral of 1 dx and the integral of e to the 2x dx. So the integral of 1 is just going to be x. And the integral of e to the 2x is going to be e to the 2x. And then using our reverse chain rule here, we're going to have divide by 2. And then, of course, we still need our constant of integration. And that's it. That's all we have to do for this one because we weren't given an initial condition.